So, we are told that in the black hole, a new space will open in the future history of the universe. It is widely believed that our universe originated 13.8 billion years ago, and everything started with the Big Bang. Eventually, the universe began to expand. Galaxies formed, stars born, planets formed. In one of these galaxies, the Milky Way, life arose. By this time, life had evolved to a point where people began to think about the origin of life and its place in the universe. But what if everything we know about the universe is wrong? What if the Big Bang wasn't the beginning of the universe? And what if we find in our world something other than the result of living in a black hole from the main world? This nonsensical theory suggests that if black holes in our universe give birth to babies, then our universe may simply be the product of another black hole. But what is the basis for this claim? What does it mean if we live in a black hole? Join us as we delve into the new theory that the big city is wrong, that we've always been inside a black hole. Turn back the clock. Before man existed, before the earth was formed, before the sun rose, before the galaxies appeared, before the sun rose the light, there was the Big Bang. This happened 13.8 billion years ago, but what about before that? Many physicists say that there is no before. They argue that time began at the time of the Big Bang, and science has no idea what happened before that. We will never know what reality was like before the Big Bang, what created it, or what exploded to create our universe. These ideas are beyond human understanding. But many scientists disagree with this idea. These physicists think that just before the Big Bang, all the mass and energy of the universe will be compressed into a very dense but tiny particle. Let's call it the seed of the new world. The seed is believed to be very small, perhaps 1 billion times smaller than any particle that humans have ever seen. And yet this particle can create other particles, not just the entire galaxy, the solar system, the planets, and all the people. If you want to call something a God particle, that's right. So, how is that seed made? One idea, many years ago, even by Nikodem Poplavsky of the University of New Haven, is that the core of our world was created in a very deep furnace, the most dangerous environment in nature, in a black hole. Before going any further, it is important to note that in the last few decades, many theoretical physicists have come to believe that our universe is not the only universe. Instead, we may enter a multiverse, a collection of separate worlds, each with its own sound that shines through the dark night sky. This led to the idea, popularized by Stephen Hawking, that whenever we create a black hole in our universe, it can create a microscopic universe that can only be seen by an observer passing by. The point at which a black hole falls was our universe formed by a black hole in some kind of progenitor universe, and is a new universe born every time a new black hole is created. But what is the reason behind these concepts? Yes, that is very interesting. A characteristic feature of a black hole is the presence of an event boundary, a region that shows very different information about something outside and something inside. Outside the region of a black hole, an object can feel its own vibrations, as the space around the black hole is curved, but it still occurs if it is moving too fast or too fast the right way. They do not fall into a black hole, but escape the black hole's influence. When an object crosses the edge of the event horizon, it immediately dies and appears in the black hole's singularity. Because the fabric of space-time inside a black hole is very curved, when an object reaches within seconds of crossing the infall zone, the mass of the black hole increases in work. For anyone outside of the fallout zone, a black hole appears to form and grow larger and larger over time. What does this have to do with our universe, though? If you were to take all of the known measurable forms of matter and radiation in the observable universe, you'd have to add up all of the following. Normal matter made from protons, neutrons, and electrons, neutrinos, ghostly fundamental particles that rarely interact with normal matter, dark matter, which dominates the universe's mass but has so far eluded direct detection efforts, photons, or particles of light, which carry energy from every electromagnetic event throughout cosmic history, and gravitational waves, which are created every time a mass moves and accelerates through the curved fabric of space-time that at the farthest limits of what our instruments can possibly detect. We can see up to about 46 billion light-years away in all directions. If you add up all the energy from all of these forms throughout the entire observable universe, You can arrive at an equivalent mass for the universe using Einstein's most famous relation, E equals mc squared. Then, if you'd like, you can ask a rather profound question. If the entire universe were compressed into a single point, what would happen? The answer is that if you compress a large amount of mass or energy into a single point, a black hole will form. The amazing thing about Einstein's theory of gravity is that if this mass has no mass and no energy, it doesn't rotate or spin with no angular momentum. The total mass is the only factor that determines its size. A black hole has what astrophysicists call the Schwarzschild radius. It is worth noting that the Schwarzschild radius of a black hole and the mass of everything in the observable universe are the same as the observable size of the observable universe. This knowledge seems to be a coincidence and raises the question of whether our universe is actually inside a black hole. But this is only the beginning of the story. The deeper you go, the more interesting things become. In the mid-1960s, a discovery changed our understanding of the world. A shower of rain and an omnidirectional shower of low-energy radiation came from all parts of the sky. The temperature of the radiation is the same everywhere and is now determined to be 2,725 Kelvin, a few degrees above absolute zero. The radiation is very black-blue and seems to have a warm thermal origin, which is about 1 part in 30,000 if you look at the sky. This radiation, originally called the primeval fireball and now known as the cosmic microwave background, represented critical evidence that our universe is expanding and cooling because it was hotter and denser in the past. The farther back we extrapolate, the smaller, more uniform, and more compact things were. Going all the way back, this picture of the hot Big Bang appears to approach a singularity, the same condition found at the central interiors of black holes, where densities, temperatures, and energies are so extreme that the laws of physics themselves break down. Something remarkable happens when you look at the equations that govern a black hole as well. If you start just outside the event horizon and escape to an infinite distance away from the black hole, you'll find that your distance, r, goes from the Schwarzschild radius to infinity. On the other hand, if you start just inside the event horizon and track your distance from the black hole to the central singularity, you'll find that same distance, r, instead goes from the Schwarzschild radius to zero. Big deal, right? No, it actually is a big deal for the following reason. If you examine all the properties of space outside of a black hole's event horizon, from r to infinity, and compare them to all the properties of space inside the black hole's event horizon, from r to zero, they are identical at every single point. All you have to do is replace the distance r with its reciprocal 1/r, or more accurately, replace all instances of r over r with r over r, and you'll find that the black hole's interior is mathematically identical to the black hole's exterior, that it's almost like taking a spherical orb that's 100% reflective, a perfect mirror, and noticing that the entirety of the universe that's located outside of that sphere is now contained, albeit distorted, in the mirror image that's reflected on the spheres. Surface.as our understanding of the universe has improved and refined in recent decades. 2 new discoveries have shaken the foundations of the planet. The first is globalization. Instead of emerging from independence, the world seems to have been shaped by the speed and intensity of the expansion of the settlement before the fortress. The shape of space gave it the internal energy to expand itself, causing the planet to rise, and when the rise ended, the big explosion began. The other is dark energy. As the universe expands, it shrinks, and distant galaxies are moving away from us at faster speeds. Again, but in a smaller way, the world looks like it's a kind of energy that's still in space and doesn't want to be diluted even though space is still expanding. People suspect that if inflation and dark energy are present, there may be a connection. The fact that there is a large difference between the rate of expansion of the universe in early and late times can be explained by inflation and dark energy. But this is only a partial answer to the question. Another part of the question concerns the mathematical structure of inflation and dark energy. Both are similar to the equations of black holes. Here's the bottom line. There's an amazing symmetry between black holes and the universe, especially when you think about what these objects look like at different times.